Hey y'all, welcome to 4.6, approximating with local linearity. We are almost done with Unit 4, thank goodness, but today we're going to be doing this. So the important thing with approximating local linearity is to understand that the tangent line of the function f of x at x equals a given point, can give you an approximate value of f of x for points close to x equals a. So I'm going to draw this out for you guys. So basically, all right, so let's say that this is your A point, right? And you have a point, let's go like right here. Let's say this is B, your B point, and based on the line tangent to A, which again is like derivative, guys. Based on the line tangent to A, you can like try and approximate said point B over here as close as you get. And you want to try and choose, of course, the closest point that you can find or is given to approximate, because, of course, the closer you do that, the closer your answer will be to what it actually is. It will not give you an exact number. And it's the same thing when going down. Let's say this is A, and let's say we're trying to find this point here. You're going downwards. And I'm drawing this bit out for you because there's another thing you have to understand with concavities, or whatever this is called when it's concave. So concave up, right? For it to be concave up, y double prime, or to the second derivative, must be greater than 0, and y double prime must be less than 0. And that's how you're able to find whether or not it is negative or positive, or which is concave up or concave down. And so when it comes to approximation, because of the way these lines are drawn, concave up will always be an underestimate. And you can see this based on the drawing. Like, here's the point here, and there's the line here, all right? There's the line. And it's going to be a bit under because of the way the line is drawn, and because of concave down, it's always going to be a bit of an overestimate, right? And I hope that makes sense to you visually. All right, cool beans. That's what you really need to know. So we're going to go ahead and do a cute little practice problem, which is right down here. The function f of x equals 5x minus 2x to the third minus 2 is concave down at x equals 1. Find the tangent line of f at x equals 1. This is kind of a throwback to an older unit, but basically, first thing first to finding the tangent line, of course, is taking the derivative. So let's do purple. We're taking the derivative of f of x. So f, let's get a skinnier thing here. So f prime x is equal to 5 minus 6x squared. All right, that gives you f prime of x. And with f prime of x, in order to do this, all right, let's backtrack a bit because I'm confusing you guys. Just so you remember, we have something called point slope form. Point slope form, which is y minus y1, or 0. You can see it written sometimes m, and we know that m is slope, or at least we hope we know m is slope, x minus x to the 1, all right? And when you're trying to do a tangent line, you're going to use what you can to get to that, basically, all right? And so, again, remember how a derivative is rate of change, derivative is a slope, and we're trying to find the tangent line of f at x equals 1, and in order to complete this point slope form equation, we need to find the slope, and we need to find, or let me highlight this, we need to find the slope, and we need to find the y, which we are about to get into right now. First thing first, this first step right here is going to be for finding the slope. All right, this is part 1. I'll put a 1 here, or 1 here. This is for finding the slope, all right? So 5 minus 6x squared, that's f prime of x. Now and it's asking at x equals 1, so we're going to plug in 1, f prime of 1, we're plugging in 1, which gives you 5 minus 6, 1 squared, which gives you negative 1. Which gives you negative 1. And negative 1, and that's going to be our slope. All right. Now we need the second y, or not the second, we need the y value, because right now, let me get a different color. If we're trying to make a point, we have the x, which is 1, but we need to find y. In order to find y, we are just plugging in 1 back into the original equation. So f of 1 equals 5 times 1 minus 2, 1 to the third minus 2, 5 minus 2 minus 2, that gives you 1. All right, so the point is going to be equals the y value. That's the y value at x equals 1. All right, so once we finish this up and we actually write our tangent line, we have everything we need to fill it in. I also highlighted the wrong y, guys. I apologize for that. I'm just now catching this. The y that should be highlighted, I will highlight in pink. This is the y we're actually looking for, because in point slope form, that first y stays the same. It doesn't move, doesn't change. All right, so we have y minus y1, which is just 1, equals negative 1 x minus 1 again. And that is basically your equation for the tangent line. I will say you can rewrite it as y equals, gotta do some quick math, negative x plus 1, which is the same thing as y equals negative, got ahead of myself there, y equals negative x plus 2. Same thing, chickies. And basically, what is the estimate for f 1.1 using the local linear approximation? Or for f at x equals 1, you basically plug in the 1.1 into that lovely little equation. All right, so we're plugging it in. So we have f of 1 equals 1 minus 1. 1.1 minus 1, this is 1.1 minus 1, equals 1 minus 0.1, which is equals 0.9. Should be 0.9. And it's saying is an underestimate or an overestimate. And based over here, let's pick a different color. Over here, it's told us it's concave down. We know based on this picture over here that concave down is going to be an overestimate. So it's overestimate because concave down. And yeah. Okay, that is all for 4.6. Thank you.